Okay, this is predominantly for the 8th grade because they're a little bit more advanced in the graphing part of this, but I wanted to talk about the explanation of flattening the curve again, now that you've hopefully have gone through the Unit 4 on graphing linear functions. First off, I hope everybody is safe. I hope everybody is somewhat taking some time and reflecting upon being home. I know it's really difficult times, and probably people have had it at this point. I am sure there are financial things going on, people losing jobs and that kind of thing, and which is terrible. There's no doubt about it. Those are unintended consequences of what has occurred here. But I'm just kind of trying to explain a little bit of the math behind the science and why some of the steps that we have been taking have been very effective, and tough decisions by our government officials have been made based on science and the math behind it. And so I know this is tough. I know being home is not good. I know parents probably out of work, not good, all of those things. But the other consequence of massive death and terrible illness is what we've tried to avoid, and they have successfully avoided a ton of it, which I will show you with the math behind the curve and the explanation behind it in a minute. But so for 8th grade, last year, you 8th graders, I spent a ton of time graphing basic lines with the constant of proportionality and understanding what a line would do on a graph, and you know, the putting in your data and how you would graph those numbers, and whether it would create a straight line going through 0, 0, which we learned last year meant that there was a constant rate of change. And now in 8th grade, the unit we just finished, or you should have finished, was linear functions. And that is, again, a constant rate of change making a straight line. So I wanted to show you a couple of documents that would show the difference in those things. And then I'm going to turn the camera back to my desk and go over some examples, and then go right into how this relates to the COVID-19 outbreak, and how the scientists are all saying, the doctors and that have been advising our government officials about flattening the curve, and what that really kind of means in our terms, simple math terms. I am not a math genius, but I am finding all of this data information very interesting, very relevant. When all you kids ask me, oh, am I ever going to do this again? When are we going to use this? Why would I ever know how to graph a line? You might never know how or have to graph a line or graph this exponential function, but now that they're on TV and they're telling us they're basing their decisions on this graph and what the numbers and the data is telling the world to do, at least you'll understand it. Or maybe you'll find it interesting and go into this kind of field of science and math and how it's all related in the real world. Okay, so my next segment is going to be just a brief overview of the functions, and showing you what the graph of the curve and what it would do or not do, and what we have done to try to mitigate, or as the doctor said, stop the spread of this infection. And to be honest, what we have done so far has been effective. The staying home and all these issues that we have done has been effective. We have done what the scientists have told us, a month ago. If we do these things, this will happen. And I want to show you what happened. Okay? Give me a second and I'll turn the camera. Got my Dotson shirt. I have an old Dotson shirt on, but I wanted to wear a Dotson shirt. It's one of my math shirts. I got some of the formulas on it. Okay? Hope again everybody's hanging in there. Okay, real fast. For all you math whizzes. So, this is just a sheet I printed that has the different types of graphing functions. First one was our constant function, which is kind of what we've learned in 7th grade. It's just, it has a straight line kind of thing. The second one is what we're doing in both, actually 7th and 8th grade, is a linear function, straight line, constant rate of change. Okay? Absolute value is similar to a linear function, but absolute value means you have both positive and negative sides. And then this one is called a step function, which we would learn eventually. It's how things change over time, but it like stops and starts, and so on, okay? The graph of the viral infection is called an exponential function, which happens to be down here, all right? And things that grow exponentially, excuse me, raise this up, excuse me. An exponential function means something that the change, your x value, is in your exponent, and it grows at a very quick rate, and it like zoops up very high. Often used in things, you may hear, oh, the fire grew exponentially. Forest fires grow exponentially because they just like spread very quickly. It's a very quick action. Things like investments, charge card rates, when you're paying your bills over months of time, that they grow exponentially. Okay, so I wanted to just show you the difference of them all. Notice there's a ton of different graphs and functions, and this is upper high school level math. I couldn't even tell you half those. I don't remember any of it, but for our basic principles of what we're learning, what you have learned already and what you are learning, and making it into the real world. Okay, so let's do a quick review of basic graphs. So again, the linear function, y equals mx and y equals mx plus b. Y equals mx starts at the 0, 0, right? Goes through the origin, where y equals mx plus b will, now that you've done unit 4 for sure, the b is the y-intercept, and it starts, the rate of change is constant. The slope is that rate of change, that letter m, and that rate is constant. Okay, so that's why it makes that straight line. So if I was to just sketch any kind of graph over here, like for instance, a bank account. Let's say you open up account with, you have $100, and every week you add $25 to it. So 25 times x plus 100. So if I was to just kind of imagine what that would look like on a graph, this side would be the money, the y-axis would represent the money, and this would be the weekly deposit. Where did I start? I opened the account with, let's say, $100, so it's already starting up at 100. But this account would have a constant rate of change of increasing at $25 per week. So at week 1, it went another 20 up to, let's say this is additional 125, so it increases slightly, and so on. And that rate would be very constant, okay? You're going to dots all the way up there. So you could just count off your weeks on the bottom. Of course, you would do this very accurately in a piece of graph paper, and your rate of change would be $25 per week, okay? Constant rate of change. The virus has not done that. It has done an exponential growth, which is much more rapid. So I want to show you what an exponential growth would look like on a simple graph, okay? Here's an example of an exponential growth. It's y would equal some number, and the x is in your exponent place. So I made up an example, y equals 2 raised to the x. So if I had to graph or chart out the points, I'm going to start just in the positive zone. If the x is 0, so 2 to the 0 in rules of exponents, anything to the 0 makes 1. If x was 1, 2 to the first is just 2. If x is 2, so I'm doing this in order, 0, 1, 2. So 2 to the second, that equals 4. 2 times 2 is 4. Keep going in order. 2 to the third. 2 raised to the third, so the x is the exponent, is 3. So 2 times 2 times 2 is how much? 2 times 2 is 4, times 2 is 8. Okay? Next one would be to the fourth. 2 to the fourth, all right? 2 to the fourth. 2 times 2 is 2. 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, get the concept? Go to the fifth. So 2 to the fifth, okay, it's not 2 times 5, it's 2 multiplied 5 times. So technically I'm going to multiply 16 times 2. 2 times 16 makes what? 32. Okay, so my graph of this would be, I would start at 0, 1 right here, all right, and then over to 1, if this is my x is the 1, over 1 up to 2. Over to 2, I would be up to 4, where 4 would be about, okay? And then over to 3, if 3 is there, I would be up to 8. You notice how it's increasing much quicker? So if this was 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8. So it's going up much quicker, okay? And then over to 4, at 4, I go all the way up to 16. So 16 would be way up here or so, right? If I kept counting on the axis, and then keep going up to 32. So this is growing what we would call exponentially. It's like a curve, and it's going at a much rapid growth. It is not linear. Linear is a constant growth, where exponential is a quicker growth, okay? Interest rates, loans, car loans, those kind of things like that are more on the exponential growth, okay? Than a straight linear. This is definitely 8th grade, linear, straight line, understanding that completely, constant rate of change, whereas this was an exponential rate of change. Now, you are going to watch a video I'm going to post that I want you, the man explains a lot of this, and you can see the differences, and I'm going to ask you some questions. Fascinating on how he models it with some graphics of how the disease spreads. So it's great to watch. Okay, having said that, what did they mean by in an exponential growth? So if I take my little sketch here, eventually on an exponential growth, okay, eventually the exponential growth will max out, and it'll get up to some point and then eventually turn and come down. Okay. So what did the disease, or what is the thinking behind this, the rate of infection rates, and what they noticed? Now, what the scientists did or noticed was, of course, it started in China, and then it got to Europe, and they were watching Italy and how quickly it was spreading and overwhelming their healthcare system. And that was the goal, was to slow it down so that the healthcare system wasn't going to be, was able to handle it. Okay, so that's when they came up with the terminology of flattening the curve. So if we take a look at my little sketch here, what they were doing was tracking the daily number of cases on the y-axis. Okay, and then as those cases kept going up and up and up very quickly, okay, over days since the first time they started tracking it. They were like, holy cow, we got to keep an eye on this thing. So it was growing so quickly. That's when it becomes the definition of a pandemic, which is an outbreak, pandemic outbreak with no intervention, no stopping, or no control of it. Then it just keeps going really, really fast until enough of the population, like 100% of the population has caught this disease, then bam, we quickly go down. So as quickly as it goes up, it will quickly go down. When we hit, this would be the max, when the whole population of the world has been infected. Okay? Now, obviously, if that was the case, massive amount of death, massive amount of problems will, be the consequences of this kind of growth. Okay? So what scientists had determined that somewhere down here was the line that hospitals would be able to handle. If we hit that number, hospitals, our local hospitals in our societies, our cities, our towns, our villages, wherever in the world, that was the line that, okay, if we get to here, we're going to be able to handle it. If we go above that, the hospitals would be overrun, and there would not be medicine, healthcare, doctors, beds, respirators, all those things about those things that they were terrified that we weren't going to have in place. So while this thing was growing, the politicians, the leaders, however you want to call them, were trying to get ahead of it. and get like things in place to handle this rapid growth. And in the meantime, the scientists were saying, well, how do we slow down this rapid growth? And the way to slow it down, they determined scientifically, was to not spread it. And how was the best way not to spread it? Was to mitigate. The mitigation word that they used was to make people stay home. If you stayed home and you weren't out around and coming across other individuals and spreading this. Now, the craziness thing of this disease was people were spreading it without even knowing they had it. And that's an underlying antidote for this disease that was something that they weren't expecting. Okay, and it was kind of a sneaky thing that right away that people were spreading it without even knowing it. And they realized that as the scientists were studying it. Okay, so thinking of that curve, I found another graphic online. I like the way this was. So if you look at this, number of people infected is all in this pink, right? Healthcare capacity. So if this is where the healthcare, meaning hospitals and all that, they could handle it if we get to here. Once we go above that, this would be horrible. This would be chaotic, tons of death. Society would be just really lost, okay? In the world. We're not talking just in the United States, we're talking everywhere, all right? With the rules in place of mitigation, social distancing, that's what they call the mitigation, okay? Mitigation. With the rules in place of mitigation, schools closed, businesses shut, trains and all that, everybody stop what we're doing, socially isolate ourselves, get away from everyone, stay home and everything else. It slowed down that growth. Okay, so this is days. This would be over days. So it slowed down that spread, and therefore we were successful in all those things we did. We were successful. Now, New York City and Yonkers, Westchester has such a high dense population that just being in close proximity, if just to do a graph of just our area would probably be pretty interesting to see, because we probably got up a little bit higher than what we wanted to. And that is why, like, the president sent in the big Navy ship, the hospital. He set up hospitals in Central Park. We set up all these different facilities to handle that if we got a little bit out of control, that the healthcare had some backup places and extra doctors and nurses and so on, because they were terrified that was what was going to happen. So in New York City, we probably got a little bit above where we wanted to, but we didn't certainly go to there. And the only reason we did not get to there was because people took responsibility and did the social distancing. So now we're at a point like, okay, do we loosen up and let ourselves relax and come back out and be more social again and run the risk of this thing going crazy again? Now, in the meantime, people that did get sick and have the antibodies and all that other science behind that, that's a whole other different, part of this. But this is what they meant by flattening the curve. Let's take the mitigation exercises, and from years to come, they will be studying this. You will study this when, those of you that go on to college and do any kind of math or science. This is historic. This is what we did, the United States did, the world did in slowing down this infection. Is it done? Not at all. So the whole science behind the infection going into the next, through the summer into the fall, we are still in the middle of it. We were successful so far, so my opinion here is science is true. The math is true. Understand the data, understand why this was successful, understand that it did work, and let's continue our thoughts and our decision making based on the science and the math, because that's true. The science and the math, there's no playing here. Okay? The YouTube video I have posted and some of the questions, students, for you to answer are thought-provoking questions. When you watch the video, don't get upset or flustered with the man's formulas and all of that. I really am not worried about you guys understanding the formulas. You will learn that some future day in high school. It's not about that. It's just understanding the basic math and the graphs and his little graphics of the little people and how the socialization and how it did spread. And maybe you'll understand why we're all still sitting home watching Netflix or doing whatever it is that you guys do or playing your video games. But this is why math and science are very important in understanding real world and things that go on. So for all you kids out there that say, I hate math and all that, you know what? Just understand the basics. It's real life. Okay? So I hope this kind of helped a little bit about flattening the curve and kind of putting a picture and a simple explanation into what we have done so far in staying home and social distancing and being socially responsible has been effective. It has worked. We have not overrun the hospitals. We have not caused massive death. There has been death, I'm sure, and I feel terrible. I know personal people myself. Someone has been affected by this for sure. It's historic, but at the moment we are managing to be as safe as we can. Okay? I hope this helped a little. The two videos that I'm hosting, one, Exponential Growth and Epidemics, is only about 9 minutes. It does have a lot of equations in it and numbers. I'm not concerned that you understand every bit of that numbers and the equations, other than the fact that he shows you that if the number of the constant changes, how much rapidly the growth of the virus would be, depending on that number and the change in the number. Just kind of watch the models, the graphics of the little virus people and how it rapidly expands and grows is pretty good graphics, so you can kind of understand the pictures behind that. In the end, he has a saying, which it's funny, I think he should start with the saying. It says two sayings, and in quotes I would say repeat these and something to think about. But if no one is worried, that's when you should worry. And the other line was, the only thing to fear is the lack of fear itself. So people are afraid of unknowns. And this is all like part of understanding this concept that is going on. So kind of keep that in mind. The only thing to fear is the lack of fear itself. If you understand things, you may not be as fearful. So take a look at these two videos. And in the end, I'm going to put a little assignment for, this would be the after the next unit, is to reflect on the videos and try to write in your words what you learned from the videos and the difference between a linear function, a linear graph, straight line, versus an exponential function, and how this is relevant to what's going on in the world today. Okay? Just to share with you, since this all began in March, I started jotting down the numbers of the rate of infection, positive infections, and deaths in both New York State. First I started with the world, then I did the United States, then I did New York State, then I was keeping track of the data of Westchester and then Yonkers, and filling it in for the whole month. Not sure what I'm doing with this, but I could put this in some kind of graphing calculator and come up with, I'm sure, an exponential curve based on the rate of the growth and so on. But it's been interesting in tracking Yonkers. I wish I could track it a little. They don't seem to release that all the time. But as of today, today's the 30th, in Yonkers alone, there's over 5,000 cases. Probably more like 5,100 cases. In somewhere in this, if I put it on a curve, it would definitely see that the numbers are slowly coming back down on that exponential growth, and therefore we have did the proper mitigation and are slowing down the rate of the infection. But New York is a hotbed, and probably based on, because we have such a close proximity in population, and this is where it really, you know, kind of started in New York or on the East Coast anyway. So watch the videos. Don't be overwhelmed by the numbers and the formulas. Listen through that. Look at the graphics he shows you and how if changing a numbers, the rate just slightly, greatly changes the outcome number. And that was our whole goal. And hopefully this helped you kind of visualize or conceptualize the whole idea of this flattening the curve concept. Okay? Stay healthy, stay well, stay in, keep yourselves safe, and hope to see you soon.